Hello students, now we'll start with the fourth module of our course Fundamentals of Artificial Intelligence. Okay, so fourth module is about planning in artificial intelligence. So planning is simply thinking before acting. What are the actions that we should take in order to perform an action? So in artificial intelligence, planning means deciding what actions to perform and in what order so that a proper goal can be achieved. So let us understand this concept with a simple example. Suppose your goal is to reach the college. You don't randomly walk around, right? You plan for everything, when to leave home, which route to take, whether to use a bus or bike. So similarly, an AI system also needs to plan before taking the actions. Without planning, an AI system may behave randomly and fail to achieve its proper goal. So, in short, planning helps AI systems act very intelligently and purposefully. So in this fourth module, we will be going through these each and every concepts, that is definition of classical planning, algorithms for planning with state space search, planning graphs, other classical planning approaches, analysis of planning approaches, and then hierarchical planning. So this module is more about understanding the basic concepts rather than solving the equations or doing some algorithms like etc. Okay. So, planning is a course of action and which is a key requirement for an intelligent agent. So, the right representation for actions and states and the right algorithms can make things easier. So, if you are imagining a robot in a room and whose goal is to reach a door, okay, and if the robot does not plan, it may hit obstacles and it move in circles or it will waste so much of time. So, but if it is planning properly, it will choose the correct steps as well as it can avoid obstacles and also it can reach the door very efficiently. So, what does planning do? Planning will help to reduce the unnecessary actions. It will save time and can reach the goals very correctly. So in real problems, the number of possible actions can be very large. Okay. So writing each action separately is not practical. So in order to solve this, we use PDDL, that is Planning Domain Definition Language. And this allows us to describe actions in a general form, represent thousands of actions using one action schema, as well as avoid writing special rules for each and every problem. So basic PDDL handles the classical planning, and as I said, PDDL syntax is inspired by Lisp or it is based on Lisp programming language. Okay. Then closed world assumption means that if something is not mentioned, it is assumed to be false. For example, if we say that truck one is at Melbourne, and then we assume that truck one is not at Sydney, Delhi, or anywhere else. So PDDL mainly follows unique name assumptions also. That is, truck 1 and truck 2 are different objects. Okay, so this distinctiveness will simplify the reasoning in classical planning. Now we'll see which are the fluents which are not allowed in a state. First one is at x comma y. Second one negate or. So in first case at x comma y there are two variables. So variables are not allowed in a state. Next one is negate poor. There is a negation. So that is also not allowed. Next one is at spouse Ali Sydney. And in this case there is a function. So functions are also not allowed. Spouse is a function. That function is not allowed. So states must contain simple factual statements only. Okay. Now we'll see the next topic, that is action schema. So action schema represents a family of actions in AI planning and it describes an action in a most general way. Okay, it represents a family of actions and it is defined with action name, variables, preconditions, and effects. Preconditions and effects are conjunctions of literals, that is, it can be positive or negative. So, as I said, the action schema contains action name, parameters, preconditions, and effects. So, if we look into one example, travel by bus, it is an action schema, whereas travel by bus from Kochi to Trivandrum is a special action or specific action. So, in this slide, we will see the example for fly action schema and ground action. So, action schema is fly P, comma, from, comma, to. P is the plane, from is the source, and to is the destination. So, you have two preconditions. That is, plane P is at airport from, and P is a plane. Then from and to are the airports. Okay, and you have fx at P from at P2. That is, plane leaves from and plane reaches to. So this describes mainly a flying action, not a specific one, right? So next one is ground action. That is, fly P1, comma SFO, comma JFK. So P1 is again the plane one, the name of the plane. SFO is the source airport, and JFK is the destination airport. So when we replace parameters with the actual values, we get a ground action. Okay, that is what it is written in this example. That is pi P1, comma SFO, comma JFK. In action schema, it is generic, whereas in the ground action, you will have a specific or actual values. A ground action A is applicable in state S if its preconditions are satisfied, and every positive literal in the precondition must be present in state S. Every negative literal in the precondition must not be present in the state S. All positives should present in state, and all the negative values should not be present in the state. Executing an applicable action A in state S produce a new state. Start with the current state and remove fluents in the delete list and add fluents in the add list. So an action can be executed only if all the required conditions are true, all the forbidden conditions are false. If this is satisfied, the action is called applicable. And if we consider a layman example, you can start a bike only if fuel is present and key is available. Otherwise, you cannot start a bike. Okay. So now let's explain this with the help of an example, fly action. That is state transition formula. Result S comma A is equal to S minus del of A union add of A. Del is delete operation and add is addition operation. Okay, S is your state. So after an action is executed, the state changes, and this is called state transition. So that is what written as a state transition formula. Okay, result S comma A. S is the states and A are the actions. Okay, S minus del of A, that is delete some actions, union add some actions. This mainly means that remove the old facts and add the new facts. Okay. So if we consider this example, you have action, remove fluent, and add fluent. Okay, first one is action, second one is delete fluent, and next one is add fluent. First one is the action is fly P1, comma SFO, comma JFK. Plane P1 is flying from SFO to JFK. That is, SFO is your source and JFK is your destination. And now I want to remove the fluent P1, comma SFO. Okay, P1 is my old fact. So I am removing P1 is at SFO. Okay, and now I'm adding my fluent, that is P1 is at JFK. Okay, so in the first case, I'm removing my old fluent or old facts, and then I'm adding my new fluent or new facts. So far, we saw some basic concepts of classical planning like ground schema, fly action schema. Now we go to into the next topic, that is planning domain. So planning domain and planning problem. Planning domain means that it is a set of action schema defines for a planning. A planning problem is defined by adding initial state and goal state. I will have my initial state and then I will have my goal state. And in order to reach from my initial state to the goal state, I will move through different uh, intermediate states or preconditions and actions. So, as I said in my layman example, that is, in order to reach our college, okay, that is your goal. You will plan for each and everything, right? When to leave home, which route to take, and whether to use a bus, bike, or car. So, you will plan accordingly. So, your initial state is your to leave from home, and your goal state uh, is the reaching college, right? So in between that, you will decide which route to take and your means of transportation. So likewise, in this planning problem also, you will have initial state as well as goal state. So a planning domain contains all action schemas. And plan a task is to find the actions which take us from the initial state to the goal state. So initial state is a conjunction of ground fluence, that is the init value. And what is the initial state and closed world assumption? Okay. Initial state lists all facts that are true initially. Okay. And whereas closed world assumption, any fact not mentioned is assumed false, applies to all states in the planning. So in the initial state, all the facts are true, whereas the facts which are not mentioned are considered as the false state. So the planning is a conjunction of literals, that is, it can be positive or negative, and it is introduced using the keyword goal. For example, if you are looking into this layman example that at C1, SFO and not at C2, SFO and at P, SFO. This means that cargo C1 should be at SFO, but cargo C2 should not be at SFO. Okay, the planner searches for sequence of actions to satisfy the goal. In order to reach a goal, some actions should be satisfied. Okay, in this example, one is a positive literal and second one is a negative literal. So here in this case, C represents cargo, JFK and SFO represents the airport names, and P1 and P2 represents plane. Okay, so how will you read that? This one at C1, SFO means that C1 is at SFO, second one C2 is at JFK, and plane 1 is at SFO, plane 2 is at JFK, C1 is cargo, C2 is cargo, P1 is plane, P2 is plane, JFK is the airport, and SFO is again another airport. So these are my initial state. Okay. Whereas my goal state is that C1 is at JFK and C2 is at SFO. My C1 cargo 1 should be at JFK airport and my C2 cargo should be at SFO airport. Okay. In order to reach from my initial state to the goal state, what are the actions that I should perform? Okay. First action is that I should load C, P, A. Okay. So what are the preconditions? C should be at A and P should be at A. Okay. And C is the cargo, P is the plane, airport is A. Okay. Effect is that C is not at A and C is in B. This means that cargo should not be there in the airport and cargo should be in the plane. Okay. Next, after loading, I should unload, right? So again, you have preconditions and effect. That is from cargo is in P. Okay, cargo should be in P and plane is at airport and I have cargo as C, plane as P and airport as A. So if I am having these preconditions, what should be my effect? Effect is that C is at airport A and C is not in the plane. Okay, so after loading, I performed my unload operation. Now I had to perform my fly operation. Fly operation, what is my goal state? C1 is at JFK and C2 is at SFO. Two cargoes should be in the separate what airports, right? So in order to get my output or in order to get my goal state like that, I'm going to perform my fly operation. That is, plane should fly from a source destination to final destination. That is, I will again have preconditions and effect, which means that P is at from. Okay, P is at from. From means first airport, and plane is P, airport is from, and airport is to. Next one is my fx. What are, if I am performing this preconditions or if I am having this preconditions, what are my fx? Okay, what are my fx? P is not at from. Okay, I will not having my P or plane is will not be in the from destination where but it will be in the to destination. That is, P is not at from and P is at to. So this is one of the example for air cargo transportation problem, which means that you will have an initial state and goal state. In order to reach from my initial state to goal state, you will perform so many actions with the help of cargo, plane, and airport. So you have again three actions, that is load, unload, and fly, in order to get my goal point. Okay. So when a plane flies from one airport to another, all the cargo inside the plane goes with it. And in first order logic, it would be easy to quantify over all objects that are inside the plane. But PDDL does not have a universal quantifier, so we need a different solution. Okay. The approach we use is to say that a piece of cargo ceases to be at anywhere when it is in a plane. Okay, the cargo only becomes at the new airport when it is unloaded. So it really means available for use at a given location. So as we all know, when a plane flies, all cargo inside it moves along, right? Since PDDL does not support for all statement, this behavior is handled indirectly. Another example for planning domain is Bloch's world problem. That is, one of the most famous planning domains is a Bloch's world, which means that this domain consists of a set of cube-shaped blocks sitting on an arbitrarily large table. The blocks can be stacked, but only one block can fit directly on top of another. So another, will have a robot arm which can pick up a block and move. It can move to another position, either on the table or on top of the another block. So the blocks world problem consists of blocks on a table as well as a robot arm. So there are mainly two rules. That is, only one block can be moved at a time, and it cannot pick up a block that has another one on top of it. So main goal is that to get block A on B and block B on C. So we have mainly two rules. That is, only one block can be moved at a time, and all block must be clear to be picked up. Okay, so this is my start state. I have three blocks A, B, and C, and this is my goal state C, B, and A. And I will have a robot arm in order to pick up each and every blocks. As we saw in the air cargo transportation problem, here also I will have initial state and goal state. That is, A is on the table, B is on the table, C is on top of A, and A is a block, B is a block, C is a block. B should be clear, C should be clear, and table should be clear. And my final goal is that A should be on top of B and B should be on top of C. So, um, So I have again two actions, that is move action as well as move to table. In order to complete my actions or in order to reach my uh, goal state from initial state to the goal state, I have to perform two actions, that is move and move to table. So with the help of these two preconditions and effects. Okay. When I perform these move and move to table actions, I will get my goal state. So my typical goal is that put block A on block B and put block B on block C. And this will be carried out with the help of a robotic arm. The challenge is to find the correct order of actions. Okay. So in this first part of our module, we saw what planning is, what is classical planning, and what are the different assumptions, what are states, what are the actions, and planning domains and problems. And we saw two examples, that is airport cargo transportation system and blocks world problem. So in short, planning allows AI system to think before acting. So this completes our module 4 part 1, and we'll see in our next video.